Today we will discuss weighted graph, shortest path and Dijkstra algorithm. Dijkstra algorithm is the one very important application of graph theory which is used to find out the shortest path between two vertices from starting vertex to ending vertex. So first we discuss what is the weighted graph. A weighted graph in which a non-negative real number w of e is assigned to its edges e. The number w of e is called the weight or length of the edge e. So now what? For example, we consider a graph This is your A, B, C, D, and suppose this is the E. If we assign a non-negative real number to each edge, which is called the weight of the edge. Suppose this is 3, this is 4, this is 5, this is 9, this is 2, this is 4, this is the 1. So such type of graph is known as the weighted graph. From weighted graph. Now today's our task is to find the shortest path between initial vertex to ending vertex. So in finding the shortest path, the initial vertex is always denoted by A and final vertex is denoted by Z. Now our aim is to find the shortest path between A to Z. There are so many paths exist in this graph here because this is the undirected graph, simple graph. So what are the paths between A to Z? First is A to B, B to Z. The length of this path is 2 plus 2 equals to 4. Another path is A to, suppose this is the E. So A to E to Z equals to 3 plus 4 equals to 7. Another path is A to E to C to D to Z equals to, this will be 3 plus 9 plus 4. A to E is 3 and E to D, sorry, this is the C point here. Okay, so here A to C to Z equals to 3 plus 7. So A to C, C to D and D to Z equals to 3 plus 9 plus 4 equals to, it is 16. And lastly A to D to Z equals to 1 plus 4 equals to 5. So these are the various paths between A to Z. Now our task is to find the shortest path among these paths. So we see the shortest path is here 4. The shortest distance is 4 and the shortest path is A to B to Z with shortest distance 4. Here the vertex set is very small, A set is very small, but we have large number of vertex and large number of edges. Then in this case it is very difficult to find out by this method. This is known as the observation method for finding the shortest path. So when the graph is very large, then how we find the shortest path between two vertices? Then we use Dijkstra algorithm. And this is the very most important application of graph theory, to find the Dijkstra algorithm, to find the shortest path using Dijkstra algorithm. Now we discuss this is the weighted graph. Okay. Now what is the weight of a path? Let G equals to V comma E be a graph. The weight or length of a path in the weighted graph G is equal to the sum of weighted of the edge in the path. What is the weight? Now the weight of this path is 4. The sum of weight of all edges. So how many edges here? A to B and B to Z are edges, and their sum is gives the length, gives the weight of the path. Okay. Similarly, we have this is the weight of path for this is 7, this is for 16, this is for 5. Now what is the shortest path? Shortest path between shortest path between any two given vertices of a weighted graph is defined as the path of minimum weight or path of minimum length. Now, just we see here ki which one is minimum among this path. The 4 is the minimum among them, so that the shortest path of this graph will be A to B to Z. Now we discuss the Dijkstra algorithm. This is the one very important application of graph theory, is to find the shortest path of minimum weight or length. That means to find the shortest path between any two given vertices of a simple weighted graph. For this we use Dijkstra algorithm. For this we use Dijkstra algorithm. In shortest path, we always call the starting vertex as A and the final vertex as Z. That means we have to start the path from A and we have to end at Z. The sum of weighted on its edges gives the total sum of path P, and we have to find the shortest path. That means the path, so here what is the P? Here is the P equals to, we denote this path as a P. This is the P. We have to sum of the weight of its edges is minimum from A to vertex A to vertex Z. That means we have to path which is the minimum distance from A to from Z. So there are two situations, different types of shortest path problem. First is shortest path between two specified vertices, and shortest path between all pair of vertices. So for first shortest path between two specified vertices, we will use Dijkstra algorithm. Now, what are the Dijkstra algorithm? This is a very important question. In examination mainly ask explain the Dijkstra algorithm to find the shortest path, or example based on shortest path using Dijkstra algorithm. Now, what are the steps involved in Dijkstra algorithm? The shortest path between two specified vertices. So here we are taking vertex A, and here we are taking the vertex Z, and we have to find the shortest path between A to Z. The following are the steps in a graph in Dijkstra algorithm. Step 1. Consider the starting vertex as A and denote it, we denote this is the point as a starting vertex A. Let P equals to A, yani ki we are generating a path P equals to A, because we are starting how many vertex, what vertex will be in the path. First we have to find. So we are starting vertex is A, so we generate a path P equals to curly braces A, and we create a subgraph for this one, T equals to V minus A. V is the vertex set, okay, and for the subgraph T is generated by eliminating the vertex A from vertex set A, from the vertex set. So let P equals to A and T equals to V minus curly braces A. Then for every vertex T in T. Now this is T into T. For the remaining vertices, we calculate L of T equals to W of AT, and this is the known as W of A of T is known as the weight of edge from A to T. Where W of A comma T is the weight of the edge joining A to T. That is, if we define W A comma T equals to N. N is the number which is the weight given on given edge. If it will be N, if A and T are adjacent to each other, then we put a number, the N, capital N, and capital N is the number which is given on given edge. Okay, if they are directly connected, then we put N. Otherwise, if they are not adjacent to each other, then we put infinity. If E edge is between them, then we put, if E is not as between them, then we put infinity. Otherwise, we put capital N here. If no edge is incidence on A and T, that is A and T not directly connected or not adjacent to each other, then we put infinity. The simple example is, suppose this is the any graph. Okay, A to B, C, D, and this is the Z. Okay, here A and C are not adjacent to each other. So what is the length of A comma Z equal to infinity? Suppose this is 2, 3, 4, 3, 9, 2, 1. Here A and Z are not directly connected. That means they are not adjacent to each other. So we put A comma Z equals to infinity. But what will the value of A comma B? The A comma B will be 2 because they are adjacent to each other. So we put W of A comma B equals to 2. Okay. So similarly we can find the W of A comma T for all other vertices, and where T belongs to capital T, and capital T is the subgraph of G, or which is obtained by removing one vertex A from V.